So our third and final webinar of the day is Reactor Segmentation, Planning the Dismantling of AECL's Legacy Reactors. CNL respectfully acknowledges that the CRL site is located on the unceded and unsurrendered territory of the Algonquin Anishinaabe Nation. We recognize and appreciate their historical connection to this land, and as the customary keepers and defenders of the Ottawa River watershed and its tributaries. We also recognize and appreciate the contributions that all First Nations, Métis, and Inuit people have made and continue to make in shaping this land we now know as Canada. We acknowledge, respect, and seek to better understand the unique Indigenous history, rights, and title on the lands where we work. Before we kick off, a few logistical things to note for those who weren't on the other webinars. There is simultaneous interpretation. You can listen in French by clicking the globe icon on the bottom right on the bar on Zoom. We have an hour for this webinar, about 35 minutes for the presentation, and then we'll do some Q&A. Please use the Q&A icon to submit your questions at any time throughout the webinar, and we'll get to them at the end. We will be recording this session because we post on our CNL YouTube page afterwards. And if you experience any technical difficulties, please email ermstakeholder@cnl.ca. We're also looking to evaluate our webinars, so we will be sending out a quick email afterwards with a quick 10-question survey. We'd really appreciate it if you take the time to share your thoughts on the webinars. Today's webinars, the host of the third and final webinar of the day is Alan Taylor. He'll be sharing some information on the recent reactor segmentation work at CNL. Without further ado, Alan, over to you.
Great. Thanks, Mike. Just do a quick check to make sure you can hear me okay.
Yep.
Great. So thanks for joining, everybody. This is exciting. We get to share the good work that we've been doing. So a little bit of background on myself. I've been with CNL and AECL now for over 30 years. I've had the privilege of being able to work in operating reactors, do the commissioning of some new builds, and now I find myself in the decommissioning world. So it's been an interesting journey, and to be part of the the overall life cycle of these units. And I find it important that we put good plans in place in order to close the life cycle of these reactors and put these incredible machines to bed, so to speak. What we're going to do today is we're going to do a sort of high-level overview of our strategy and our planning that we're putting in place in order to safely segment our fleet of reactors. So this is the first reactor segmentation webinar. We're hoping to have a few more as our program matures and we grow. But today we're going to cover 4 basic topics. We'll talk about our mission, why we're here, what we want to accomplish over the course of this work, give you an overview of what reactors we are going to be dealing with as part of the portfolio, discuss a little bit about our strategy, how we put our plans together, and then we'll go over at the end an overview of a dismantling concept for one of the reactors. So we'll start with our mission statement. Every good mission needs a strong mission statement, and for reactor segmentation, we're responsible for the development of the standardized approach to address the dismantling of 9 legacy AECL reactors. So what does that really mean? That means that we are going to put a lot of effort up front into studying the differences and the similarities of the units that we have. We put together plans and work with other teams and experts on how to develop specialized tooling in order to take these units apart. We will oversee the dismantlement when we do get into the field and start to segment the reactors. And then finally, make sure that the material is guided into the appropriate waste paths. So once the reactors are dismantled, we can be assured that they're in a safe interim storage environment. All right, let's do an overview then of our reactor locations. So we have a short video clip here that'll demonstrate where our portfolio lies. I can give you a spoiler alert. There are units that are in Ontario, units that are in Quebec, but we also are covering the other two reactors that AECL is responsible for, the NPD reactor and WR1. Just want to be clear, though, that NPD and WR1 do not fall into the reactor segmentation portfolio, but this video points out where all our locations are. All right, we'll start off in the beautiful Ottawa Valley and the Chalk River site. So at Chalk River, we're looking at the two units that are still installed within the facilities, and that is the NRX and NRU reactor. The NRX, NRU are both research reactors, built, designed back in the 40s and 50s and have run as recently as 2018. We also have in the portfolio the two Maple 1 and Maple 2 reactors. These were isotope producing reactors that were in operation from 2000 to 2008. And then additionally, staying in the Chalk River area, we have 3 legacy calandrias which were removed from service back in the 50s and 70s and now lay to rest in the waste management areas. We have an NRX1, an NRX2, and one of the calandrias from NRU. Talked a little bit about NPD. NPD is located very close to the Chalk River site. As I said earlier, it's not part of our portfolio, but I think it's important to highlight that it is one of the reactors that AECL and CNL are working on the decommissioning for. Out in lovely Manitoba, we have the WR1 reactor. And then flipping the script back to the reactors that fall within the reactor seg portfolio, we have the Douglas Point reactor, which is in Bruce County, out at the Bruce Power site. This is one of the this is actually the second in line of the CANDU prototypes prior to the Pickering and Bruce reactors that were built shortly after. And we also have a unit in Bécancour, Quebec, Jean T1, which is a unique design. It was a boiling water CANDU prototype. This unit is located on the banks of the St. Lawrence River. All right, so we'll shift to a bit of an overview of a comparison of the reactors. So we've had a chance to see where they're located geographically, but let's go over a few points about a comparison between them. So starting on the left side at the G1 and Douglas Point site, those are located off-site of Chalk River. And then we have the NRX, NRU, the Maples, and the 3 legacy waste units. They are in the Chalk River site. The units that are titled in blue are installed in their bioshields. A bioshield is essentially a large, heavy-duty concrete structure within a robust building. That's where the reactors are located. The other 3 units in the legacy waste category, those are placed in legacy areas of the waste management zones at Chalk River. When we look at how we go about moving waste, once we start dismantling these reactors, the Douglas Point and G1 sites, we'll have to utilize public roads to move specialized containers. But for the other units, all the movements of material will be within the CNL, the Chalk River lab site. For the movement of the waste, we make sure that we are using specialized containers designed for purpose. and moving them to approved storage areas. And then from an approach standpoint, the approach for the units that are within their bioshields, we're going to call in situ segmentation. So that's essentially dismantlement of the reactors within the area that they reside currently. And for the buried units, it's a retrieval with remote segmentation. And so what that really means is, building an engineered structure over the top of the units as they lie, and then dismantling them in the area and placing them into the approved packages. All right, let's talk a bit about strategy then, and how we've developed our plans on where we are now and where we need to go in the future. When it comes to developing strategy, there's certainly multiple items to be considered, but today we're going to talk about 6 key aspects that we've put in place in order to develop a strategy output. So those are review of records, modeling. We're going to talk about collaboration and benchmarking. We're going to talk about technology, what our waste options are, get into a discussion a little bit about optioneering or best available technique study that we do. And then I have a video that's going to show some of the good work that we've been doing from a from a categorization standpoint. When you bring in those strategy inputs, then they lead you to a strategy output that we believe will be successful for us to complete the portfolio of work. From a records and modeling standpoint, what we're meaning here is that we take a lot of time to review and go over our records. And the records being things such as operational records from when the facilities were running. We're looking at drawings, we're looking at construction drawings or any modifications made to the facility. Really, it is to gain an understanding of how these units were constructed. If you think back, for units like NRX, these were constructed back in the late 40s, going into the 50s. The Douglas Point site and the Gentil site were built primarily in the 60s. So we have to go through the records and ascertain all the information that we need in order to make intelligent decisions on how we move ahead. So a big component of our work is reviewing these records and looking at the historical operation. And from a modeling standpoint, we're going to talk about 3 primary methods of modeling. The first graphical representation is a neutron analysis. So what we're looking at is we're looking at neutron activation, or the study of the radioactivity properties of the materials. When reactors are running, the metal components are, they're subject to a pretty intense neutron flux. So what happens is the material becomes activated. And we have a very smart team of experts at the CNL sites that do modeling for us to help us understand, how radioactive these components may be, and to drive us in the right direction of how we're going to deal and plan with the segmentation. On the top right-hand side, we're using 3D modeling or additive printing. So essentially what we do with that is we take our existing drawings and we input that into our computer software. And then from there, we have specialized printers that allow us to actually print renditions of our reactors themselves. So this is a great tool from a standpoint of both understanding the layout and what opportunities or challenges you may have when we're disassembling the units. But it also helps us with regards to public engagement, gives people a good feel of the size of these units and a scale version and how they're laid out. And then finally, on the bottom right, we have a team of experts at work here at CNL that are doing digital renditions, so digital twinning. Basically, that is something new to us, but what we're doing is we're taking our information that we have on these reactors and we're creating very detailed and sophisticated models. These models are fantastic when it comes to putting our plans together. We can input all sorts of criteria into them, including activity modeling or radioactive readings that we get when we're in the field. to help us put together a safe and robust plan. And once again, it's another tool that's very valuable from sharing what we're about to do with the public, and it gives you an idea of the units, how they looked, how they're laid out, with a real benefit towards understanding. Our second key component with regards to our strategy inputs is collaboration and benchmarking. So we're not the first country in the world to do this type of work. So it's important for us to learn from our counterparts. We have collaboration agreements set up with Germany, France, the UK, and the US. No one in the world has yet to do a can-do reactor, but we glean lots of information. We share information and lessons learned with our collaboration partners and learn from them, and we can put that into part of the planning on how we dismantle our reactors. So it's key that we maintain a robust collaboration and benchmarking effort to stay up with modern practices, to share information with our colleagues, and to glean it from them. With regards to technology, there's no one-stop shop for how you dismantle these units. We know we're going to be dealing with material that could be heavily activated or highly radioactive. So the luxury of handing a set of hand tools over to some capable workers and asking them to go in the field and dismantle these units, it just doesn't exist. We will be using remote technology, robots, tools, etc., that will allow us to work in a safe environment, in a remote environment, in order to segment the units. And the three primary methods of actually dismantling or cutting these steel objects are mechanical. Think of things such as circular saws or diamond wires, which is essentially a wire saw that's embedded with a diamond encrustment, or shears or snippers. We can also use thermal tools, and these thermal tools work on the end of robotic arms, and they allow us to cut thick pieces of metal or components remotely and safely. And then a relatively new technique in the decommissioning world is the use of lasers. So high intensity, heavy energy lasers can be used as well to cut these metal components. All of the units could be used depending on the type of challenge we have, and there are pros and cons to both. With mechanical, tend to be lower cost, but more reliable. But with that, you also create quite a bit of particles. You've got vibration, which can affect the robotic arms, and you do create a secondary waste. If you think about using a table saw to cut some wood at home, you end up with a nice cut plank, but at the same time, you usually end up with a bucket full of sawdust. So you get the same type of idea with a mechanical cutting. Thermal, they're nice vibration-free tools that have limited effect on the robots, but they could be complex to support. You've got to be careful of the volatile discharge of the gases. And obviously you're dealing with high heat, so heat and fire are part of the issues from a planning standpoint. And then finally, lasers. The pros to lasers is you can have fantastic control on your cuts. You can use unique end effectors on your robots to get into very cumbersome spots that you may not get to with a mechanical device. But the cons for laser are complexity. And they do have a higher cost initially when it comes to purchasing and installing these units. So if you can take the three ideas for cutting, our strategy is to use commercially available and in-house tools. We have a very strong team at CNL that has already developed the expertise on operating and maintaining and constructing tools in-house. We have some teams here that are experts worldwide for building bespoke tools that are used on can-do reactors. So we are utilizing and leveraging that so we can focus on issues and solve these issues with our in-house expertise. Additionally to in-house work, though, we are looking at commercially available tools. There are a number of tools commercially available for this work. As I stated about the mechanical thermal laser cutting heads, we also plan on utilizing off-the-shelf robotics. There's a number of companies over in Europe and the Far East that build very specialized and capable robots that will handle our cutting tools. So it's a real sort of circle environment here of using commercial tools, in-house tools for the cutting technology. So with regards to waste, there are options on how we handle our waste when we start segmenting these reactors. All of our waste and how we package it and move it is governed by very robust procedures and the use of pre-approved packages prior to dismantling. So think about it this way. Once we're in the field, prior to completing any cuts, we will have a number of different options of containers to choose from. And we'll fill those containers based on how we want to transport them, where they are going for interim storage, where they may be going for direct disposal, and I'll talk a bit about that from a commercial standpoint, and making sure that they are robust and approved for road transportation. When you segment reactors and dismantle reactors, you're going to primarily be dealing with what we refer to as intermediate level waste. So this is waste that requires special handling and requires special packages, and we utilize those as we dismantle the units. Our two primary options for waste paths are to interim storage at the Chalk River site, and we're also investigating the possibility of using supply chain. There are companies that do deal with radioactive waste. They work with the utilities and work with other areas. And they have the capabilities of taking our waste directly and then processing that in a more of a disposal mode. So as we put our plans together, we have to have a good understanding of what the material is going to go into and the modeling, other items such as characterization, which I'm going to talk a little bit about in a couple of slides, help us drive our waste path. And we will send our waste down the appropriate path based on those decisions. Another aspect of putting a strategy together is to utilize a best available technique or a optioneering process. Really, in a nutshell, what this is to identify the challenge that we have in front of us, and then we pull together a formal collaboration of experts that we have in-house. So we're bringing in waste experts, we're bringing in reactor segmentation team experts, we have mechanical equipment development experts and characterization, etc. So there's a number of different groups, and the best way to describe this is it's essentially a sort of professional brainstorming, so to speak. We identify the problem, and we define what our scope is, what our boundaries are, constraints, assumptions, etc., and identify attributes. And then at that point, we are essentially meeting to throw any and every option that we can come up with on the table. We've seen upwards of 24 options that have come out of these brainstorming discussions. But it's important that we need to whittle those down to 2 or 3 really viable options. And we do that by, really challenging and breaking down the ideas and scoring these options against attributes that we've previously identified. These attributes may be things such as, how easy is it to access the components, or, do we have the ability to put these directly into a container, or do we have to do a little bit of processing prior to? So a number of different things. But essentially, once these attributes are scored, and we've added weighting factors into it, we'll end up with a result on what our best approach is on segmenting and dismantling the units. All right, so our final attribute with regards to strategy is characterization. And characterization has really been what we've been up to for the last 2 or 3 years. So we have had teams at the Chalk River site and at the Douglas Point site and G1 site putting together and pulling samples out of the reactors themselves. Now, the goal of characterization really is sort of twofold. Once we retrieve these samples then are sent to a laboratory to be analyzed. And then the information that's gleaned from the analysis will then be used to decide on a number of different things, such as how are we going to decide on which path the waste takes, but yet also how are we ensuring that we're protecting the worker and the environment and understanding the hazards that are involved. Additionally to that, the characterization output will help drive the design of our tooling. We can understand how radioactive a component is, and that may allow us to decide whether or not we need super specialized tooling, or can we get away with something that's more simplistic. I'm going to run a short video now on some of the characterization work that we've been doing. The video does pop between units, so I'll preface the video before it runs with that. You're going to see some of the work that took place on one of our buried legacy units in the waste management area. And that includes a mock-up of in-house tooling that we constructed to dismantle a mock-up reactor. And then you'll also see some clips on work that's happening in the NRX reactor, the Douglas Point reactor, and the Jean T1 reactor. Start off with the buried units at Chalk River. You can see we're using computer building. And our workers in the field that are starting to perform the excavation to get to the reactor, and then ultimately pull the samples out of the unit. And this particular unit is what's referred to as the WMAX in-house, but it's the original NRX calandria that came out in the 50s. You can see some tooling that we used that allowed us to breach the reactor walls and insert some video cameras to get information about how the reactor looks in its configuration. Additionally, we've taken some samples of the material and some readings. And this is the mock-up using a Brock robot. We built a mock-up, placed it in one of our areas in a clean environment, and this is allowing us to see what works and what doesn't work with regards to robotic disassembly of the units. Shifting inside, got a lot of work going on at the NRX reactor, coring holes, taking metal samples, taking concrete samples, gaining information about the graphite that is installed in the units and other materials. A lot of hard work going on by dedicated team members to pull this work off, and it's been exciting. Had a few challenges, but overall it's been really good work for everybody. Here we're utilizing a combination of off-the-shelf equipment and specialty design tools. And you can see a video of the camera going through the concrete core and then eventually into the walls of the reactor itself. The Jean T reactor, we've done some internal scrapes, measurements of the fuel channels themselves. We got video of going up into a fuel channel, take some readings, gain a lot of information about how the reactor is configured. Once we get our samples out, use a chain of custody to take the samples, take some information from them, and then we ship them safely out to a lab for analysis. Douglas Point, we have a team that's down there actually as we speak, doing some characterization. But prior to doing the characterization work that was more intrusive, we used one of our little specialty robot crawlers to go into the vault and take some video, give us an idea of what the current status and how good of a shape, or in this case, perhaps not the best shape, the units are in right now. So you're looking at the bottom of the moderator dump tank of Douglas Point. And then finally, at Douglas Point, we're in doing samples of fuel channels and gaining information about the radioactivity within the unit itself. Pulling out some of the core samples. There's a video of what it looks like inside the vault. That's the calandria of the Douglas Point unit, which shut down in about 1982. It's also important to note we are doing, working with the teams at the sites to do a lot of housekeeping and cleanup of some of these facilities as we undertake the work prior to the overall decommissioning of the units themselves. Right, great. So we've talked about the 6 inputs into our strategy, and what they drive then is a standardized or a holistic approach to how we want to deal with these units from a strategy standpoint. For the installed calandrias, thinking back to the slide that did the comparison, we're looking at doing in situ segmentation that aligns with the fuel channels. So what does that really mean? Well, we have reactors that are installed within the concrete bioshields, and each one of these reactors have a number of internal pipes where the fuel component or the uranium component of the reactor resided. These we find are in either a vertical or a horizontal configuration, and we are going to take a look at our dismantling following the axes of those fuel channels. So we start with removal of the rod assemblies, and once those are removed and packaged up safely, then we move into remote segmentation using robots for the calandria themselves. Calandria is also, it's essentially a large tank. And then once, all components are removed and packaged, the waste is transported to its proper waste storage or disposal area. What are the benefits of doing a standardized approach for installed calandrias like this? We get to utilize the existing biological shielding. So when these reactors were engineered and constructed, they were designed to protect the workers in the environment while operating, using heavy, thick concrete and steel shielding, and we'll continue to utilize that shielding in order to dismantle them. So this helps us keep the dose low for workers. It's flexible and scalable across multiple platforms, as we have challenges based on different reactor types, and locations. This allows us to plan the utilization of similar tooling where applicable across the different units. And it does allow us to work concurrently if we have the ability to do so and we're ready. We can work at alternate locations. Standardized approach is a little bit different for the buried units. We will segment the legacy waste calandrias at the site that they are currently located, where we will build environmental protection into it. So we will make sure we have, properly designed and vetted containment. So once we start the unearthing of these units and the segmentation, any type of contamination or whatnot is kept in a controlled environment. We will remotely and segment these units at the field and package them there, and then remove those off to a suitable waste area, with the end result being an environmental remediation of that particular area. What are the benefits of doing it this way? Well, we have robust environmental protection. We have great containment, and we put that in place. Allows us to execute a timeline which is optimized. Once again, low dose to workers, protection to the environment, and this capability then is transferable for one unit to another, as the legacy waste calandrias themselves do exist in different areas at Chalk River. All right, so finally, let's talk a little bit about dismantlement and a dismantlement concept. So what you see here, we'll use Douglas Point as an example. So this is a rendition of the Douglas Point reactor itself. So Douglas Point was a 200 megawatt CANDU prototype. Think of it as the little brother to the Pickering sites or the Darlington sites, etc. And it's installed within the concrete bioshield, as I've mentioned on a couple of slides. How do we go about dismantling the unit? So let's look at a dismantling sequence. At a very high level, what we do with regards to dismantling units such as Douglas Point is, first of all, start with the removal of the reactivity mechanisms. When a reactor is built, not only does it have containment for fuel or containment for water, there are a number of components that are used to ensure that the reactor is safe to operate and is controllable, and we refer to those as reactivity mechanisms. So these are essentially the items that were used during operation to make sure the reactor was functioning properly. Those would be the first items that we remove, segment, and package. Then from there, we're looking at the removal of the calandria and pressure tubes, starting with the pressure tubes. Mentioned earlier in one of our strategy outputs that we're going to work on the fuel channel axes. And what that means is that we are developing tools using in-house expertise to pull what we refer to as the fuel channels out of the reactor. So at Douglas Point, there's over 300 fuel channels, and they're made up of zircaloy pressure tubes and calandria tubes and some very heavy end fittings. And we have tools that we will dismantle those channels with, remove them from the reactor itself, and then place them into suitable packages. Once the fuel channels are removed, then we move on to the actual dismantlement of the calandria shell. The removal of fuel channels involves quite specialty bespoke tooling, whereas when we get into the removal of the calandria shell, we're now switching gears more into a dismantlement method that you perhaps would see more in the commercial areas. Essentially, cutting tools, placing tools in the unit itself to cut using heat. Perhaps it's lasers, it could be mechanical shearing, but essentially we're going to look at cutting the calandria shell into small manageable pieces, and place those in appropriate packages. Once the calandria is removed, then we're left to remove these very robust and heavy end shields. On each end of Douglas Point, you have about 3 feet of very thick carbon steel shielding, and we'll utilize mechanical tools such as diamond wire to segment these components into smaller pieces and place them into packages. And then finally is the removal of what we refer to as the dump tank. One of the operational requirements for Douglas Point was that the water that is inside the calandria had to have a means to escape, as was all part of their control and safety mechanisms. And the water was essentially, dropped down into a dump tank, which resided directly underneath the calandria. The dump tank itself, we expect that to be, less hazardous radioactively than the calandria itself, but it's still a pretty heavy piece of kit. Has its own properties and nuances we need to deal with, but we'll cut those up, segment them, and put them in waste containers. So essentially, if you think about it from a dismantling standpoint, you deal with some of the control components, you pull the fuel channels out, then you dismantle the calandria itself, or any of the other ancillary systems or support mechanisms around it. And we can use this concept for not only Douglas Point, we can utilize similar tooling at the Gentil 1 site, and then similarly at Chalk River, look at doing the same for the NRX and NRU as they reside in situ. So that pretty well covers everything with regards to developing strategy and giving you an overview of how we would go about segmenting these units. It's a lot of work, it's exciting work, and it's interesting. And it's certainly fraught with some challenges and opportunities. But I'll open it up now for any questions that we may have from our viewers.
Okay, great. Thank you, Al. Awesome presentation. Lots of work going on. We will get to the Q&As now. So with all those reactors on the list, do you have a set kind of timeline on which ones you're going to tackle first?
Yeah, great question. We do. And am I still there, guys? Because my computer.
Yep, I can hear you.
Okay, great. Yeah, for sure, we do. And it's taken us a little bit of going back and forth on what we felt is the best approach to dismantling the reactors and how we want to align them from a strategy standpoint. We plan on tackling off-site the Gentil 1 reactor first, and there's a couple of reasons for that. One of them is to do with the fact that the reactor itself didn't operate all that long. So we anticipate, and our modeling is reflecting this, that it's lower in radioactivity. So it does make sense to plan our tooling and tackle the Gentil 1 site first. What we learned from Gentil 1, we can take that and apply that to the Douglas Point site. Douglas Point ran for a significantly more time, so we know we're going to be dealing with higher activity, and we want to be confident of our approach. So offsite, Gentil 1, Douglas Point. In parallel at the on-site, we're going to be tackling one of the buried units first in the waste management area, and then moving on to some of the other buried units, the Maples, and then NRX and NRU. From a time frame standpoint, we're looking at progressing work within the next couple of years out towards the end of the 2020s. By the end of the 2020s, we should be at the Gentil 1 site. Takes about 4 to 5 years of work at each site to complete that work, and then we'll shift gears, potentially wrapping up at the late 2030s.
Okay, thanks. So what's getting all these reactors under one umbrella, what's the biggest benefit to that approach?
From a holistic standpoint, what is allowing us to do is it's a couple of things. First of all, in addition to the work that we put up with collaboration and benchmarking, we're adopting a lead and learn approach on how we dismantle these units. And what that means is, as we, progressively move forward, we're continually taking our lessons and understanding of how we've done the work, and then adding robustness to our next steps for the next reactors. So we can look at the work holistically. We can see the big picture, so to speak, of all the units that we have, and the team then has the ability to take a look. Okay, will the approach for Joan T work with NRX, for example? Perhaps it will, perhaps it won't. Will the tooling work from Joan T over to Douglas Point? The team can gain an understanding by looking at the view from the big picture. So that results in safer practices. It works in better utilization of resources. It works in a better business model from the amount of money that you would spend on tooling. You can incorporate all of that into the big picture.
Okay, and then to kind of to add to that, so with all those reactors under that umbrella, is there a reason why WR1 and NPD aren't part of that?
Yep. Yeah, it's a great question. The reason for that was decisions that were made a number of years ago by AECL and CNL. And those decisions are that the decommissioning strategy for NPD and WR1 is an in situ decommissioning, not planning on doing a reactor segmentation approach.
Okay. Okay, thanks for that. Next question is, someone has a scale question. So the video that showed the calandria in one of the waste management areas, the video goes inside. What's the scale of that? And maybe feet, I guess, would probably be best.
Feet
Like,
or
how big is
meters?
that? Or meters, whatever you want.
Yeah, sure. No worries. It's roughly 3 meters in diameter by about 4 meters in length. So 10 feet diameter, 12, 13 feet in length.
Okay. Are there any volume reduction tooling? Are there any plans to build any volume reduction tooling?
Yep. As part of our tooling design, we have to be cognizant of the size of the pieces and how they fit into our waste containers that are available to us. And one of the criteria that you put in place is to try and be efficient as you can with volume. So you're dealing with fairly robust waste packages. But they are limited in size, and we need to make sure that we volume reduce components in order to have the greatest and best packing efficiency that we can. And volume reduction can be anything from cutting to smaller pieces to placement plans, putting together actual models on how you're going to place the material into the boxes. And it can also involve, more blunt instruments such as compression tools to size reduce tubing down to a sort of flat pack, right? So we're trying to IKEA-ize as much as we can for sure.
Okay, thanks for that answer. Next one coming in, could you remind me of the name of the robot used for the calandria segmentation?
The one that was in the mock-up is a Brock robot. So Brock is a large firm, I believe, from Sweden or Norway. They're European for sure. We have a number of these Brocks at the Chalk River site, and we have a team of technicians that are really handy at the operation of these Brocks. The Brocks come in different sizes. They have different functions, and the real value in them is that you can adapt them using off-the-shelf end effectors or technology at the end of the arms, or add our own customized tooling to them. So they're definitely a tried and true robot type of device that's used all over the world in the decommissioning environment.
Okay, great. Thanks for that. Are there any companies in Canada or elsewhere that can make laser segmentation? And what type of lasers do they use?
Ooh, that's a great question, and we're starting to get deep into the technology
Okay,
of it. I'm
okay,
not a laser expert, but I do have members on my team that are definitely more up to speed with it. Other companies in Canada, yeah, and there's companies in Europe. These are used across the world. So the plan will be, if a laser end effector is the way that we want to go, we'll make sure to vet the companies that are there, and we will make sure to purchase and utilize a tool that is going to work for us. These are very powerful pieces of kit. I don't want to quote any numbers because I'm not a laser expert, but I know these things are more than capable of cutting through, upwards of 10 to 15, even 20 centimeters of steel. So I can pull some more information on the lasers outside of this webinar, but these are, as I said, these are items that are used throughout the world, and they're very powerful.
okay, great. Thanks for that. Just a couple more here.
Mm-hmm.
So this might be a bit out of scope, might be more for waste services, but it gives us, ideas for the future on future webinars. But instead of interim storage, packaging of the waste, is it possible to do disposal ready to avoid double handling of the waste?
Yeah, that's a great question. And yes, waste and the waste operations teams are definitely the experts in this. But from our standpoint, we are certainly looking to avoid double handling. Canada does not have a disposal path per se. It's being worked on. I've got to be careful not to go too far out of scope for our work. But from a reactor segmentation standpoint, we will utilize and use what best waste path suits us. So we do have options to potentially use supply chain for some of our waste. And if we are not using supply chain, we have our internal processes which allow, the utilization of interim storage, with the idea being that we're certainly looking to avoid double handling, that anything that goes into an interim storage package is designed to, seamlessly make its way to the disposal path once it's available.
All right. We'll get to one more. Let's do
Sorry,
one
Mike,
more.
it said my speaker is not working now.
No, I can hear you. I can hear you still. So
See
you
what I
good?
can do.
Oh, you can't hear me though? All right, we'll take a sec. Okay, well, that's it. How about we end it there?
Hey, I can hear you
Oh,
now.
no, there. You're good now. Okay. Okay, we'll do
Good.
one more.
Okay.
One more question, and then we'll end it. The maple reactors, would you do both at the same time or one at a time, learn best practices from one to do the other?
Yeah. Awesome question. And it's certainly something we've discussed. Our plan with the maple reactors is we will lead and learn, which means we'll start with one. We look at what worked, what didn't work, areas that we can improve or areas that we're doing well with. And once we've learned from the first reactor, we switch gears, move to the second reactor, and help speed up the timeline, gain efficiencies, et cetera, et cetera. So yeah, great question.
Okay.
One at a time.
All right, perfect. With that, we will end the webinar. Thank you for everyone for attending. If you, even if you attended just this one or all three this morning. We really appreciate your attendance to these. We're able to share the great work that we're doing with all of you. We do want to please ask you to help us out with the short survey that we're going to send out after this session. And also a reminder that we do post to YouTube. It will take a couple of days, and we'll get to. We'll also send out answers to questions we didn't get to if some come in late. And if you have any questions at any time, email us at ermstakeholder@cnl.ca. Alan Taylor, thank you so much for your great presentation. Always great. Great work you guys are doing across the country. So yeah, any last words? Your microphone still works, right? Yeah.
I think it does. No, I just want to say thank you. It's always great to be able to share the work we're doing externally, and I'm looking forward to some more updates down the road once we've progressed on our journey. So thanks, everybody. Great
Okay.
questions.
Okay. With that, we'll take off. Thank you very much for attending. See you next time. Goodbye.